Welcome, everyone, to the March AI/ML seminar series. This is a series hosted out of the exobiology branch at NASA Ames Research Center, focused on improving the usage and understanding of AI and ML within the astrobiology community. I'm your host, Ryan Felton, and today we'll be hearing from Dr. Hamid Valizadegan from NASA Ames discussing ExoMiner, which is his deep learning classifier for working with Kepler and TESS transit data looking for potential exoplanet candidates. Hamid, please take it away.
Sure. Thanks, Ryan, for the introduction and invitation for this talk. So what I'm going to talk about today is our efforts in the last few years in using machine learning for vetting of transit signals and validation of exoplanets. So what I'm hoping to achieve in this talk is, there has been a lot of inertia in using machine learning for exoplanet application in particular and astronomy in general. So I'm hoping that I can convince you guys that machine learning is the right tool for such application. So what is machine learning? Well, in supervised mode, we are after developing a model that can receive input and generate an output. Now, this model should be adaptive, meaning that it needs some tunable parameters that can be updated using data. Now, the goal is to optimize an objective function. For example, it can be a loss, like negative likelihood, over the parameter space. The parameter space defines what the model can or cannot do, basically the flexibility of the model. The objective function is usually task-specific. For example, in classification, it is empirical error rate. This is the part that a lot of people, the applied people might not know, but we are always after developing theories that guarantees the optimality of the learning framework. So it's not only we need to develop an algorithm, we need to also make sure that that algorithm has some optimality. When it comes to application, we want to make sure that the use of the methods are correct and is correct and meaningful. And we also, in the post application, we want to analyze the result and making sense of it. So for the classification or supervised learning, there are two modes of learning. One is called batch learning. The assumption is the data comes from a stationary distribution. And because of that, we can collect data from that distribution. For supervised, that means that you have a set of input-output pairs. And we basically update the parameters of the model based on this set of data. In online learning, we do not have that stationary assumption. We assume that the data is generated by an adversary which wants to maximize our loss, and we want to minimize the loss. Basically, we play a game with the adversary. We receive a few inputs, one or a few inputs. We update our parameters, and based on that, the adversary generates a new set of examples to maximize the loss. The focus of this talk is the batch learning. Now, when we invented computers, there was no field that allowed us to work with computers. So basically, the tools that we had was coming from neuroscience, statistics, mathematics. At some point, it turned out that those tools are not enough. So that's why we invented this new field called computer science and the subfield AI and machine learning. So what I'm going to do in this talk to give you a brief, kind of overview of what we did for classification, the path that we took in order to get to where we are. To do that, so the application that I'm focusing is the transit method for planet discovery. So I assume that most of you are familiar, but if not, so in transit method, we basically take a photo of a star periodically, let's say every 30 minutes. And we measure the brightness of the star, and if the brightness of the star has a dipping that happens periodically, that could be an indication that there is a planet orbiting it. However, not all transits are due to planets. It could be due to collapsing binaries, to stars orbiting each other, could be due to a background object, a transit that orbiting a nearby star, but not the star of interest. It could be due to a stellar variability or systematics. Because of these sources of false positive, what we need to do is to develop a way to separate the sources of false positive from the true planets. So NASA has developed two telescopes that work based on this like transit method idea. Kepler, that was looking for 4 years at a small part of the sky, was collecting data, basically was taking a picture every 30 minutes. It discovers more than half, basically we discovered more than half of the existing planets from Kepler plus K2. Now TESS, that is a follow-up mission, it designed to survey a much larger space compared to Kepler. So far, it has covered 85% of the sky. The way it works, the sky is divided into sectors. The telescope photographs every sector for 27 days and move on to the next sectors. Some of the sectors have overlapped, meaning that for some of the stars, we have more than 27 worth of data. So far, we only discovered 760 planets from this from the data of TESS, but the prediction or estimation is that we are going to have 10,000 rocky planet from TESS. So I mentioned earlier that we need to find a way to separate the sources of false positive from the true planet when we are looking at the data of these telescopes. So scientists have developed these types of reports. This is called a spot data validation report, the summary report. There is a longer version of this report, which basically has multiple different diagnostic tests on it. It has diagnostic tests like weak secondary and odd and even that are for eclipsing binary. Basically, we look at these two tests to understand whether there's, the transit is due to a collapsing binary or not. There is difference image test in the middle and the bottom middle. That is for background object. There are tests for systematic stellar variability. Basically, the scientist, the domain expert, by looking at these reports, they can know whether the source of transit is a false positive or a planet. So if we want to ask machine to do the same task, what we need to do is to have a classifier that receives these reports as input and generate the class label for us. However, in math or statistics, we did not have anything that could work in this level. Basically, what we want to do, we want to input a complex data form like this report as input and develop a function f that can be applied on this and generate a label. So this was something that, even 10 years ago, maybe 20 years ago, seemed impossible, right? So, and again, so we did not have that knowledge in math or statistics to do this because this function seems super complex. We did not know how to visualize it. Now, what I'm going to propose here is the way that domain experts do this. So when you ask domain expert to do, basically to look at this report and decide whether this is false positive or not, what they do, they look at, for example, this diagnostic test, the weak secondary, and see whether there is a transit or not. Basically, what they do in their mind, they extract some features that are important for this diagnostic test. And then there are some other values that exist here. They combine it with those values and decide whether this is an indication that this is a false positive or not. So if we want to do the same with machine, we have to do the same process. For each one of these diagnostic tests, we need to have a feature extractor component. So I show you the weak secondary, which is this branch. We need to have a feature extractor. Then we need to combine it with the scalar values that is associated with that complex data form. And then for each one of those diagnostic tests, we do the same. So each one of these branches that you see is working on um, one of those basically diagnostic tests in this report, right? So I have parallel branches processing each one of those diagnostic tests. First, I do feature extraction. I combine with scalar values. Then once I do that, I combine all the features and do the classification, right? So this is something that probably is a way to understand how domain experts do this. Now, what that means, so now because I could decompose this problem into these like processing parts or components, now I can have like different functions, right? So I have a feature extractor for each one of these diagnostic form. I have a summarizer that summarizes features combined with the scalar values. And then I combine all of them and do the classification. What that means? That means that I have a very huge nested function of this form that I need to find in order to do this task. We did not know how to do this. So when we started doing machine learning, AI, or like computer science, or whatever you want to call it, we did not know how to do it. So the way we started doing this, we assumed that this connection is caught. We extract the feature from this complex data form manually. So basically, like someone see it and understand what features are important in this like image, they extract that features and then cut this part, replace those diagnostic tests with their feature that we extracted manually or automatically, and then did the next part, which is the combination or summarization. You can do PCA or whatever you want to do. Then in the end of the day, we do the classification. Once we have those, like, let's say 200 plus scalar values, the optimal classifier is Bayesian classifier. So in theory, the optimal way to solve that problem is to develop a posterior. Basically, the question is, what is the chance that my label or my signal is a planet, given I have those values extracted from the DB reports? We are talking about the scalar values, because this Bayesian classifier cannot work on the time series, right? Again, so we did not know how to do this a few decades ago. But this is optimal classifier, but it needs the knowledge of the likelihood, the form of likelihood. We need to know the prior. And once we have the decomposition, we know the form, we can basically learn the likelihood. And we need to know the likelihood for each one of the subclasses. That adds another complexity, because we often do not know what that form is. We need to make some simplification, assuming, for example, that the data is Gaussian. A lot of time this form, like people in astronomy call it the statistical versus machine learning, but this is basically the opening of any machine learning book. That's where we start doing machine learning. We always, like, the way we justify why we cannot do this, basically introducing this. And the reason it's difficult to do, so there are two ways to do that. If you want to go non-parametric, do the likelihood in a non-parametric way, you need, like for this application, we had 200 plus input. The X is a high dimension. We need exponentially more instances or points in that data, very high dimensional data, in order to understand the density. So that's gonna fail, right? We cannot go that route. So then we have to go parametric. That means that we need to make some assumption, like, let's say the data comes from a Gaussian distribution. That assumption can go very wrong. Even with that assumption, if that's the right assumption, the covariance matrix is a huge matrix for that size of the data. Then we have to make another assumption. Let's say we assume that the covariance matrix is diagonal. Or we can assume that, like, this is again another kind of opening in the machine learning books, that naive-Bayes classifier, which means that we assume that the variables are independent given the class label. Those assumptions make solving this posterior or like maximizing likelihood possible. But the problem is that those assumptions could be very wrong. And because of that, people have started solving, such problems in different ways. People, again, none of these methods come from like computer science or machine learning. Their roots are like usually mathematicians or a statistician. They develop expert system classifier. The idea was that, okay, if I'm a physician and I know how to diagnose a case, I will see how I'm checking the variables in order to do that. I develop a set of predefined if-then rules that says that, okay, if this variable is bigger than that value, then go to the next level. So basically, I have a flow chart that is mostly manually designed. You can incorporate some data, but it's mostly designed manually. The advantage is that it has an easy explanation, right? So you can read the chart and understand what it's doing. It does not need data. That's another advantage. But the problem is garbage in, garbage out, meaning that if while you are designing this flow chart, you make a mistake or you misunderstood how things are being done, then the output can be very wrong. The maintenance is very costly. So for the application of wetting these transit signals, people develop RoboWetter for Kepler, but once they wanted to apply it for TESS, they had to put a lot of efforts to make it applicable to TESS. They call it tech now. It still needs manual features. You cannot apply such like expert system on a time series or images. And it's like I said, this is not automatic. People later on develop decision tree classifier. And they develop a learning algorithm for it. So basically now you have trees like this that is data driven. Basically tells you what is the label in the end on the leaf. The advantage again is that it has easy explanation. You can understand what it does. The inference is fast. You can learn a decision tree of this form very quickly, but it's unstable, meaning that if you remove one or a few instances, your decision tree can be completely different. It also have rough decision boundary, meaning that every decision boundary is in parallel with the axis because it just works on one variable. It's usually inaccurate, and for variables with more than more categories, it's biased towards those. Again, you cannot apply a decision tree on time series or images, right? So again, we assume the features are extracted already. Another method that people early on, this has roots in neuroscience, people develop perceptron. The idea was that neuron is what a neuron does is a simple calculation. It just computes the weighted sum of the input. So people use this as another computational kind of machine, but soon people understand that it cannot solve complex problems like XOR. And as a solution, because it's just a linear kind of decision boundary, as a solution, they learn that, okay, if I do it in two levels, I have two computational neuron that computes the weighted sum of the input, and then add another neuron on top of it, and the next layer, let's say, that computes the weighted sum of the output of the first two neurons, I can solve problems like XOR. That led to the introduction of multi-layer perceptron. That is now like basically you have many layers. Each layer, the output of the neurons of each layer is connected to the input of the next layer. And as you can see, there are so many kind of connection in such network. People did not know how to solve or optimize such complex multi-layer perceptron until the introduction of backpropagation, which is nothing but like shift or propagating the gradient distance backward. People also introduced convolutional neural networks inspired by receptive fields of visual cortex. The idea was that if my input is time series or images, I do not need to, connect, or I do not need to extract features globally on an image. I can understand locally what one image means or a time series means, extract the features, and the next layer, I understand the higher level features and go forward. The advantage of this is that you have less connection now. Instead of connecting every neuron to the next layer, you just connect a kind of a local or receptive field to the next layer. So the advantage is just you save a lot of computation and make the learning or optimizing such network very fast. Another idea that was introduced like around 20 years ago was again from another statistician, Vladimir Vapnik. He said that, okay, when solving a problem of interest, do not solve a more general problem as an intermediate step. Try to get the answer that you really need, but not a more general one. What it means? What it means is that if I want to solve if I want to put a decision boundary between two classes, why should I decompose it to likelihood prior? I just put a decision boundary. Basically, I just learn a function or find a function that can separate two classes of interest or multi-classes of interest. Bertrand Russell, about 100 years ago, had a similar idea. So basically, the idea is that don't solve like a more complex problem if you know what you're after. And Vapnik actually introduced support vector machines based on that idea. The idea of support vector machine is that if I want to put a decision boundary between two classes of interest, this is a classification problem, right? I put a decision boundary that has maximum distance to the nearest examples from each class. And he has proved that maximizing the margin, and that concept is called margin, minimizes an upper bound and the generalization error. Basically, this is an optimal classifier. Now, going back to this problem, again, support vector machine cannot accept complex data forms of like a form of time series or images. Now, going back to this problem, can we solve this complex like kind of function in one step instead of separating to feature extraction and like classification? Well, now we have all the tools, right? So for feature extraction, given that my input is images or time series, I can use convolutional neural network. So I know what functional form I use for this. For combining the features extracted from the image with the scalar values, I can use multi-layer perceptron. I can explore all the combination and how to basically weight them up in order to come up with a kind of summarized feature. Once I have, then I can use a linear classifier, the problem solved. So now I have all the tools, right? I have, again, this functional form that I can visualize because I know what the form of CNN looks, how MLP looks like. And I know what parameters they have. So even though in the beginning, this nested function seemed super complex, now it's like easy to solve. But the problem is that this, as we saw, has a lot of parameters, and the question is, can we solve it? So again, we are hitting the curse of dimensionality. We have so many parameters and usually not enough data, and the question is how we can solve it. Now, in machine learning, we have this idea called bias variance trade-off. The idea is that the error can be decomposed into two terms, bias and variance. Bias is if the model is not flexible enough, either my hypothesis space or the parameter space is not flexible enough to allow me to learn the function that I'm learning, then or I don't optimize that function enough, then my error is going to be high on training and test both. And this is called underfitting. The variance is how much the model is going to change based on the data I'm using for training, right? So if my model is over parameterized or I overtrain it, then my training error, my error on the training set is going to be small, but when I use it for other data set, it's going to be high. So this is called overfitting. So what we want to do, we want to trade off between these two. We want to find a point that the model is trained enough, but not too much. So in order to do that, people invented like approaches like this, which called K forecast validation. The idea is that you decompose or partition the data in multiple folds. Let's say if it is 10 forecast validation, you partition it to 10 folds. You use 9 folds to train, 1 fold for test. And within the training, you use another subset called validation. And the idea is that you measure, you monitor, don't want to overtrain or undertrain. So you want to do it enough. Now, going back to this method that I mentioned, this is nothing but ExoMiner. So we developed this tool in 2022. The reason I took that path, I just wanted to say that this is just the natural outcome of how things should be done. So this is original ExoMiner that we developed in 2022. There were two branches that I showed earlier that we did not use because we did not know how to do this too. They were more complex than the other inputs, but we used other diagnostic tests. And if you look at the paper, what you see is a slightly different. So now we call them like convolutional branch for full orbit, for example, right? For each basically diagnostic test, we have a convolutional part. We have a fully connected layer instead of like multi-layer performance. We have one layer that was sufficient here. And this is basically ExoMiner introduced into 2022. What we showed in that paper was that this new method performed much better than existing classifier. We compared with different classifiers from deep learnings and like traditional models. Another like way to look at the numbers that indicates the performance is much better is the so let me introduce precision. So precision is what percentage of the instances that are labeled by the model as positive are really positive. Okay, and recall means what percentage of exoplanets in my bag the model could retrieve as exoplanets, right? So 96.8% means that there were out of every 100 instances that was labeled by the model as positive, 3 of them were false positive. Here it says that out of every 100 instances that were really planet, the model was able to get 97.5 of them or 4 of them. This is another one that shows the precision recall curve, PRAUC. Basically, there is for these methods, you have a threshold that you can change, and based on the change in the threshold, you can have different points in precision recall. And we show that, at any points in the precision recall curve, the model performs better than existing classifier. This is another table also shows, interrupt me anytime you have a question. I should have said this earlier, but yeah. So let me know if there is any question. So this is another table that shows what would be the recall if I choose a point in the precision recall curve that with a precision of 99%, basically this gray dotted point, which is the precision of 99%, where it cuts each curve. For ExoMiner is 93.6%, means that if I want to make sure that 99% of the instances labeled by the model as planet are really planet, what percentage of all the planets I'm able to retrieve? It's 93.6% for ExoMiner. The second best is 67.7%. For some of the classifiers, 0. It means that this classifier put a false positive in with a high, basically give a very high score to some of these false positives. That's why there is no point that you can get a non-zero recall for precision of 99%. I mentioned bias variance trade-off, and like the application is as follows. There were these question from some of the domain experts that the training set is not big enough. And, basically their idea was that there were unseen scenarios that you are not aware, and that's going to hurt the model. So what we did, we tried to reduce the size of training. We could not increase it, right? So the size of the training set was like fixed. We had that size. What we did, we randomly subselected a percentage of the training set from like 1% to 100%. And we monitored the performance in terms of precision recall and PRAUC. And you can see even with 5% of the data, the model is very robust. The precision recall did not get affected. That by itself means that the data was enough. And the reason the model behaves, so on the bottom, you see that even though the precision recall is not affected, the confidence of the model gets lower. This is the score that the model gives to each class. So this top is like exoplanet class, the bottom two are the like basically different type of false positive subclasses. Even though the precision recall did not get much affected, but the model becomes less confident. And this is exactly because of that bias variance trade-off that I mentioned, because now we do an earlier stopping, because if we do more training, the model is going to overfit. We prevent it. That means that the model becomes less confident. That's indication that if you have more data, the model could become more confident, but because the data was not enough, even though precision recall did not get affected. So basically, the model adjusts its confidence just because the data set is not large enough. We did a similar example because there was another concern that the training set, the label of the training set is noisy. So we randomly introduce more noise into the data and measure the effect of the noise. So here what I'm showing is 0% to 50% label noise of like not the whole data set, as a part of data set that are easier to get confused. And that's the main concept for the domain scientist. It's called Kepler object of interest. And again, we show that, even with 40%, the model becomes, the model is very robust to the label noise, but again, reduces the confidence. And again, it's because of the bias variance trade-off. Another idea that we developed the following year in 2023 was this concept that, we know that if a star has already planet, the chance that the new signal, the new detected signal is planet goes higher. And the existing classifier, none of the existing classifier receives as input the configuration of the star, meaning that whether already we know there are some false positive or planets around that star. So what we did, we get the input, the score of the classifier, each like multiple classifier, each separately, and combine it with the configuration of the star in terms of how many planets we discover so far, whether there are sources of false positive, and whether there are unknown signal yet. And show that no matter what classifier you apply that model, basically we train a model that receives the output of RoboVector, for example, combined with the configuration of the star, learn the label again. And we show that for in any of these classifier, the performance improves if we do that. And the result for ExoMiner is a chart like this. The x-axis shows the ExoMiner score, y-axis shows what would be the newest score based on the configuration of the star. For example, here, the first number, like each one of these, the first number is the number of false positives, the second is the number of planets, and the third one, the number of unknown signals we have for that star. For 0 to 1, meaning that there are 2 planets, 0 unknown, beside the unknown that we are checking, and 0 false positive, if the score is 0.5, The original score is 0.5. The new score, after knowing that we are facing a star that has already two planets, would be 94, 95%. And, so by doing this, we could discover 69 new planets for the system that had already, existing planet. The original ExoMiner, we also in the original paper, we used it to discover or validate 301 planets. So the total, um, of planet we discovered using this two method is 370. Now, after that, we started working on the test data. We improved the ExoMiner. We added the two branches that was missing, unfolded flux and difference image. As I said, like these were more complex to work with. For each one of these inputs, we need to do a special handling or pre-processing the data before feeding. But beside that, the architecture, the detailed architecture of these branches matter. So we needed to understand how to do these kind of things. Another change that we did later on was merging a few of these branches that are concerned with the local view of transit. So there are three branches. Other even basically look at every other transits in a chain of the transits. We secondary look at the second transit that exists with the same orbital period and the original transit. All of them are concerned about the local view of the transit. And because of that, we understood that, okay, the feature extractor doesn't need to be separated. So we merged the feature extractor part for those three views, and then basically did the specific handling for each branch separately in order kind of to address if there is any special treatment that needs to be done for that specific diagnostic test. And the result is what we call ExoMiner plus plus. And we later on actually added two new diagnostic tests, periodogram and full orbit trend data. These two are not available in the reports, in the DV reports. So people do not look at these two when they classify these transit signals to planets or false positive. But we added them, and we showed that actually these two helps quite a bit the performance. So the result is, in two papers last year, we published a paper on 2 minutes data of tests. And this year, you can find the paper on arXiv that is for the FFI data. So here I'm reporting the performance that we reported last year. So in order to build the training set, we just use that. So as I mentioned, so the tests look at different sectors, one sector at a time. So we use the first 67 sectors to build our training test set. So this is what we reported last year in the paper. In order to get the label, we use the ExoFOP TUI reliable labels. So these labels are the labels that often are obtained using follow-up study spectroscopy. So these labels are very good labels. So they are almost always right. Then we also use the TESS EB catalog from Villanova. These are noisy labels because they were just looking at the photometric data, the data of TESS to know whether the source is EB or not. This often leads to, not often, but there is a good amount of label noise in it. We also use the tech that RoboVector, that expert system technology that I mentioned, to obtain more labels. And again, it just looks at the photometric data, so it's noisy. Now we want to learn, basically how to classify this based on this set of labels. The challenge is that the ExoFOP TUI labels not only use the photometric data that comes from tests, they use other sources of the data like spectroscopy and other things. So it would be magic if we can just learn everything's there because there are some missing data, right? But we showed in the paper that ExoMiner plus plus actually, even for the cases that domain expert look at the report and see there is no sign of false positive, the model was able to classify them correctly. And that by itself means that there are some patterns unknown to the domain expert that exist and could be utilized by the model in order to classify these cases correctly. Here is a summary of like cases that we had. So there are 6.5% planets in our 2 minutes data in that paper, and 93.5% false positive. We also wanted to know how we stand like compared to Kepler. So we built also the most up-to-date data for Kepler. It had 8.6% planets and 91.5% or 4% false positive. This is the performance. So we could obtain 92.7% precision and 94.5% recall for TESS. Compared to Kepler, it's not comparable. And the first question we wanted to answer, this is the part that I was saying. So not only developing the model is important, but also understanding the output and explaining what's happening, it matters a lot. So the first question comes to my mind, did we do something wrong? Why the performance is not as good as Kepler? But after investigating cases, we understood that, okay, part of this like difference comes because the photometric data for a lot of cases that comes from exofob labels is not sufficient. So the model did not have access to anything that is that make it enable or make it possible for the model to classify them correctly. And there are cases, subcategories like SEB1 that are more in test data because there are more follow-ups. The selection of the stars in TESS in such a way that the follow-ups is easier for TESS compared to Kepler. Beside that, there is diagnostic tests are more inconclusive for TESS. Because of the short length of observation, ephemeris sometimes are not ephemeris calculation and derived parameters are sometimes long. And as I mentioned, the label is not of high quality. So overall, that means that we have a lower performance. Another thing that we did recently, we wanted to know how the model generalized to the new sector. So we wanted to get the model that was trained on the first 67 sectors and apply it on the new sectors from 68 to 94 and see how it performs. So the distribution data is very similar. We have almost 69%, 69, 68% positive examples, and but the performance is different. So if you look at the performance of the model that is trained on the first 67 sectors using 10-4 class validation, but applied on the newer sector, the precision gets a hit. So the precision, we have a 5% reduction. And the question is why, all right? So it's very confusing. Again, the question is whether we did something wrong when we were optimizing the model or no, it's just natural. And in order to do that, what we did, okay, so this is a very key point. So when we look at these signals, some of the signals we revisit again. So if the star is in the overlapped areas of a sector, we are gonna find that signal again in the new sector. So this signal was found originally in the first 67 sectors. Now we refound it in the new sectors. So if we look at the distribution of the signals between these two set of the data, there is part that is overlap. These are the signals that existed. Now we are finding them again. And if we investigate how we are doing in the intersection part and the difference part, we get some insight. The first things that we found was that the number of planets reduces quite a bit. And the reason is because we do not find KP. KP is the non-planet. These are the planets that we discovered before TESS, but now we are seeing them again, right? We are seeing signals that correspond to those planets again. Now, in the first 67 sectors, we already found all of those. So we are not finding like a lot of them in the new sector. So that's why the new signals has only 6% known planets. And that leads to reduction of overall planet in my bag. So the number of planets was 75%, in the intersection, now it's 53%. And if I look at the performance, what you can see, the performance on the intersection is no different. This is similar. The problem is the new sectors. And again, the precision is the only metric that is affected. The recall is not affected. So why is that? Well, here is a known things in machine learning. So if you have a more imbalanced data set, basically, if you have less number of positive example, even with the same data and the same model. So let's say I have 100 positive and 100 negative, and I feed the model precision is like 50%. Now, if I just remove 50% of my positive examples in random, then my precision goes down. So by reducing the number of positive examples in my bag, automatically precision reduces. And that justifies part of this lower performance, but we also have the performance that is lower in false positive. And after, like, again, doing more analysis, we understand that there are more nearby EVs, there are more SEVs. These are hard classes for the model. There are, like, the stellar fields are more crowded for the new star visited in these new kind of sectors. And so overall, the reason performance is lower is basically there is some data distribution shift between the early sectors and new sectors. The model is not doing anything wrong. It's just that the data has changed. And this is a graph shows, earlier I mentioned that ExoMiner was doing much better than existing classifier. This is the reason. Models like RoboVector or AutoVector, this is a random forest, they are only able to process or get as input scalar values. So even though these diagnostic tests are in complex time series and image form, they need to extract the features, like we trust the feature extractor that people develop and use those features as input. As you go to this side is ExoMiner plus that not only uses a lot more diagnostic tests, more comprehensive list of diagnostic tests, but also it uses as an original form. And that's why that the magic happens, that the model is much more accurate. Okay, so I'm going to stop here. This is, the code is released. If you have any question about the code, Miguel is the right person to contact, and you can access the code and use it if you need to. And these are all the people, the current team. We had a lot of interns that helped us over years. The list is very long, but this is the people who have been helping us more recently, especially for the tests work and result. Okay, that's pretty much it.
Awesome. Thank you, Hamid. That was amazing. I really appreciate it, especially going through the history leading up to everything that led up to ExoMiner, because that really is helpful. Are there any questions from the audience? You can raise your hand or type something in chat.
Yep.
Sure, go ahead.
Quick question about the linear velocity scales you're doing on the moon. Does this have any connection to the thrust vectors involved and the gravity pulls?
I'm not sure if I understood the question. It's coming very bad. Sorry. Ryan, could you get the question?
No, Christopher, could you possibly type the question into chat? It's a little hard to hear what you're asking.
I'm just basically just talking about linear velocity structures, mate. Just trying to get linear velocity structures working. That's right. I'll email it to you. Sorry. I'll email you.
Okay, thank you.
Yeah, sorry, Christopher. There's some background noise, so it's coming very badly on my side.
Any other questions? I have a few also that I can ask, but I want to give the audience a chance. Okay, well, people are thinking stuff. So I know you talked about a little bit there at the end, Hamid, and maybe this answered the question, but I was noticing back around slide 29 when you were first showing the precision and recall results compared to the other ones. I was wondering, why does RoboVetter seem to be one of the ones that was doing, even though it's the oldest on here, it's 2017. I was wondering if you had a sense for why it was essentially the second best in terms of the precision recall curve compared to ExoMiner, even though we had these other ones like ExoNet and RFC between RoboVetter and ExoMiner. Were they maybe focusing on other types of parameters to improve?
No, because it's hard to say like politically correct. So the reason is the model is developed. So there was no concept of training and test there. So they developed it using the whole data set.
Okay.
Yeah.
Okay. And then I was also wondering, with slide 34, you had these three numbers, and I was wondering if you could just clarify again, is there an ideal scenario there with these numbers that would be the key that, oh yes, this is a potential exoplanet? Because I got the sense that you could have many different combinations here. So what again is like the more ideal one for potential?
Well, there is no ideal one. So it's the
Okay.
combination of like ExoMiner score and the configuration that allow us to validate the planet or not. For example, if you are on this line, right, which has one unknown planet, and there is no false positive or no planets around it, that means that so the validation threshold that people use is 99%. So meaning that you want to make one mistakes out of every 100 planet that you validate. Now, so what it means that I need to get to the 99% point, right? So that 99% point based like which scores you have and which configuration you are working with is gonna change. So if I have three planets, even with original score of 0.5, I'm gonna be fine validating a new planet around that star. Means because I already saw there were four planets around this star, even though ExoMiner is not very confident, but because there are three other planets, now I'm going ahead and validate it. But if you go one lower, which is two planets, you need to have a higher score for original ExoMiner in order to validate it.
Okay.
Yeah.
That helps clarify it some more. So yeah, okay. And then just one last question. This is more, I guess, more forward looking. Um, obviously ExoMiner is focused on transit data. Have you guys discussed, or is there any opportunity to expand this to other exoplanet hunting techniques, like maybe something for Roman or HWO? Or is that really a complete, is that essentially building something new from scratch?
Well, you can. So there are multiple problems. So we were thinking to do it with their radial velocity, like spectroscopy. But the problem is that only a small subset of the data has a spectroscopy. And, it it seems that it's not as easy to develop, to basically analyze, um, radial velocity data. Again, so we did not discuss that a lot, but we wanted to do it for a subset of the data that spectroscopy data is available. But our domain experts in the team, like, kind of were saying this is like not easy, or at least even for transit, it was the same. So there is a need for more discussion for us to understand how domain experts do this and learn it and like code it for machine. But other things, no. If you want to develop it, as long as you have this diagnostics test available or a subset available, you can use the same model. but you need a training set too. But if any mission is just generating a different set of products, then you need to start from scratch. You can use a similar framework, but not really, same model exactly.
Okay. And Tom Green did point out that transits will be observed in the Roman Galactic Bulge Time Domain Survey. So the same data set is used for the microlensing. Okay. Are there any other questions? We're about to wrap up here. And also, let me just, so everyone knows, the recording of this will be made available there at this YouTube channel that we have. It's just the AI ML Astrobiology Seminar Series. So you'll be able to see this recording there. Are there any last questions or anything related to ExoMiner from the chat?
There is a question from Jay that he's asking about confirmed planet versus validated.
Oh, yes.
Right. So, I don't think everyone is kind of agreed on the same definition, but my understanding and like how we defined it is that validation is when you are using a statistical or machine learning model and validate planets in a scale. Whereas confirmation needs a follow-up study and you do it one or a few around the same star at the time.
Perfect. Thanks, Ahmed.
Confirmation is more kind of solid. It's very difficult to have a false positive when somebody confirms a planet.